So we were looking at independent and mutually exclusive events. Today, what I want to focus on are independent events. And these are events, if you recall our definition, that are happening kind of one after another, they're happening together, but one of them happening has no impact on the other one happening. Okay? In other words, a way to summarize this would be that no matter how many times you do this, or if you do one after the other, the probabilities will not change. Oh, A, B. All right, the probabilities will not change. We've used the example of rolling dice, okay? Every time you pick those dice back up and roll them, those are independent events because it doesn't matter what you rolled the first time, they're getting rolled again. And you have the same probabilities, all right? So what do we do when we have independent events and we want to look at the probability of both of them happening, okay? By the way, remember, we'll put our laptops away now that we're taking notes, okay? But the probability of both things happening, A and B, is going to be the probability of A happening times the probability of B happening. So if you know two things are independent, it's the probability of A times the probability of B. So let's use kind of a simple example of rolling dice again. And we're going to add up what we roll. Okay. Does anyone recall what the probability of rolling an 8 would be? Remember?
6 times 30.
Close. 7 was the most common. That's
Right.
6 out of 36.
So 5 out of 36.
So it'd be 5 out of 36. That's actually an easy way to remember it. If you remember 7 is 6 out of 36,
Bless you.
then rolling a 6 or an 8 is 5 out of 36. Rolling a 5 or a 9 is 4 out of 36. Okay? If you can't remember, that's okay. Just draw yourself the table. And getting a 2 and a 6 would give us an 8. Getting a 3 and a 5 would get us an 8. Getting a 4 and a 4 would give us an 8. A 5 and a 3 gives us an 8. And a 6 and a 2 gives us an 8. All right? So those 5 out of 36 would be the probability of rolling an 8. Okay? But that's just once. Okay? Every time we roll the dice, it's an independent event. So the probability of rolling an 8 and an 8 and another 8, since those are all independent events, is just the probability of rolling an 8 times the probability of rolling an 8 times the probability of rolling an 8. Okay? So in other words, it's the probability of rolling an 8 cubed in this case, right? So we'd have 5/36 cubed. And that's 125 over, what is that, like 46,000 something? I'm trying to remember.
I have the decimal.
46,656.
I remember there were a bunch of 6s in there. There we go. 46,656. So those are our chances of getting an 8 3 times in a row. Okay? Because rolling a 6 has the same probability, 5 out of 36, this is actually the probability of rolling any combination of 6s or 8s 3 times in a row. Okay? A 686, an 866, or whatever. Okay? All of those would have the same probability because their event has a 536. Now, if we do something other than a 6 or an 8, those probabilities change because, as we said, 7 has a 6 out of 36 chance. All right, a 2 only has a 1 out of 36 chance to be rolled. So those would be different. But with this, we could compare them. Okay, so those are independent events. They don't have to be the same event, like here, like we had here. Okay, we could also say, what's the probability of rolling an 8 and a 2? Okay. And in this case, we're talking about rolling an 8 in the first roll, a 2 on the second roll. Alright? Well, the probability of rolling an 8 is 5/36. The probability of rolling a 2 was 1 out of 36. Okay? So we have 5 over 36 times 36. Okay? 1296. Alright, so 5 out of 1296. So it works with any independent events, not just the same one repeating. Okay. Now let's take this idea one step further. Okay? And we're going to do this and also define one thing where you might be tempted to treat these events as not being independent, but we are going to treat them as though they are independent events. Here it says, in 2004, approximately 65% of the population of the United States was 25 years old or older. Okay? In a survey, 10 people were chosen at random from the population. What's the probability that all 10 were 10 years old or older? Now, we're not going to pick the same person twice, right? So we're not using replacement, correct? We pick a person out of the population. We're not going to pick them again, so we haven't put them back in the population as we choose our second person. All right, so technically we're not replacing. Will that change this 65% probability? Theoretically, yes. Okay. But how many people live in the United States?
340 million.
Yeah, over 300 million people. Is taking one out
10 probably.
going to make any difference in our probability? No. Realistically, no. It'll make 1, 300 millionth of a percent or something like that. Okay? It's not going to make a significant difference in the situation. It's certainly not going to make a difference in our answer as we round the 1 or 2 decimal places. All right? So, this is a common practice that if the population that we're pulling from is very, very large, and this is often when we're using some kind of a statistic like this to determine a probability, we can assume that each person we're picking is an independent event. Okay? The change in probability is so insignificant, we treat it as an independent event. Okay? So, let's think about this. The probability of picking someone whose age is 25 years or older is what, according to our problem? 65%. Okay, so 0.65. So what would the probability of all 10 people being older than 25 be? What?
Wait, the rest of them?
All 10. Each person we pick, that's an independent event, right?
Would it be 65 over 100 to the power of 10?
There we go. It would be this probability to the power of 10. Okay? We're repeating this. We have 10 independent events, right?
Yep.
So, if we have 10 independent events, it's going to be 0.65 times 0.65 times 10 times 0.65. All right? So, that's just 0.65 to the 10th power. Okay? Does that make sense? Okay. What would the probability that all of them were less than 25 be? Let's think about it for one person. What's the probability that somebody is...
The common.
Yeah, it's 0.35. 0.35. So what's the probability that all 10 of them were less than 25?
2 times 10.
Yeah, 0.35 to the 10th power, okay? So this is a pretty easy thing when we're looking at this in terms of what if all of them are in this category or all of them are in this category. The problem, or the challenge I should say, comes when we try to do kind of a combination of them. For example, what's the probability that half of the people were greater than or equal to 25 years old? All right, and what's the probability that half of them would be less than 25? Okay. What do you guys think initially there?
0.65 to the 5th times 0.35 to the 5th.
Okay, 0.65 to the 5th times 0.35 to the 5th. And that's great, okay? That actually is part of it. But there's a little part that we're missing, okay? Because you know what that assumes? That right there assumes we picked all 5 of the people who are greater than or equal to 25 first, then we picked all 5 people who are less than 25 after that. Okay? So what do we also have to consider? What?
Combination.
Combinations. Okay? Different ways that we could come to that conclusion. Alright? So, we actually have a combination, alright, with the 10 people, okay? We're actually going to choose 5 of them that are and 5 that are not, okay? What does that look like? Something from the binomial theorem, okay? If you remember the last question on the test,
Yeah.
I told you specifically to find the third term of that expansion, okay? That was kind of a preliminary. You already know the binomial theorem. We're going to actually look at practicing applying that to cases of probability. and it's actually an extension of that theorem called the binomial probability theorem. Okay? So, don't worry, that's right here, it's copied. Alright, the binomial probability theorem. This is for use when we have repeated independent events. But this is key, it's binomial, right? That means 2. You have to consider the situation having only 2 possible outcomes. Okay? Now, that doesn't mean that the situation has to have only 2 outcomes, but when you are considering a problem, you have to look at it in terms of 2 outcomes. For example, if I want the probability that people I picked had a birthday in August, obviously there are 12 months, but I could see that as the probability that they're born in August and the probability that they're not born in August. Okay, so all the other 11 months are just part of that second possibility. All right, so sometimes we have to translate a situation kind of like this. But we have repeated independent events, things like picking 10 people out of the population. Those 10 people, that's the repeated event. We're doing it over and over again, picking a person. Okay? And they're independent because the probability is not changing. All right? So, let's look at how we could write this. Let's say that E is our event. We'll use the lowercase letter p to represent the probability of that event happening. Okay? And then Q is going to be the complement, the probability of the complement of that event. Okay? So what do P and Q add up to? 1. Alright? It should always add up to 1. And then N is going to be the number of times that this event is repeated. Okay? So what we're going to do, we're going to, in order to find, I wrote the wrong thing here. It's not the number of times. To find the probability for a certain number of times E occurs, we need to consider the terms of this expansion. P plus Q to the n power. Okay? Now we already said P plus Q adds up to 1, right?
Yeah.
So if I just said expand this whole thing, what is it going to equal every time?
1.
1, okay? So doing the expansion is kind of useless here. But notice we said consider terms of the expansion. We're going to look at specific terms so that rather than just seeing, okay, what's the probability of having all 10 people be at least 25 or all 10 people be less than 25, we could now figure out the probability. What's the probability that I get at least, well, let's start with the simpler one. What's the probability of getting 6 people who are greater than or equal to 25 years old? Okay? The nice thing with this is figuring out the exponents for your term on your expansion is super easy. Okay? First of all, the binomial that we're going to expand is our event E has a probability of 0.65. The complement is 0.35. And then we were repeating it how many times? 10. We were picking out 10 people, right? So it's 10. So if we look at the expansion here, we know it's going to be 10 choose something times the 0.65 to some power times the 0.35 to some power. Okay? And again, the powers are easy because we want 6 people, right? To be at least 25. Well, this is the probability of one of them being over 25. So, it's to the 6th power. Okay? If I want 6 people to be at least 25, how many do I want to be less than 25? 4. So, guess what the power of 0.35 is? It's 4. And then once we know that, we can put the 4 in there too. Okay? So setting up the terms, notice this is just one term of the expansion, but if you figure that out, that will give us the actual probability that we get exactly 6 people who are 25 years old or older. Okay? See a few people figuring that out. See what it comes out to. 0.2376?
No.
Okay. And then some other decimals.
Yeah.
Okay. Alright, so you can round it to that. That would be fine. If you want to write it as a percent, 23.8% approximately. Alright? So those are our chances of getting 6 people that are at least 25 years old. Okay? Is that making sense?
Yeah.
Alright, good, good. Now, if we were asked to find a particular range, like what's the probability that we got at least 6 people who are at least 25 years old? We would just need to find multiple terms of the expansion, right? So if I wanted at least 6 people, I'd have to figure out the term for 6 people, 7 people, 8 people, 9 people, and all 10 people. And then I just add those together. Okay? Notice we can also use the complement. If we wanted at least 9 people, or I should say, let's say we wanted fewer than 9 people. Okay? What's the probability we got fewer than 9 people that were at least 25? Okay? We could do that by using the complement. Fewer than 9 that were at least 25. Okay? That'd be 1 minus the probability that we had 9 or 10. 9 or all 10 that were greater than or equal to 25. So here, we're only having to figure out 2 of the terms of the expansion and subtract it from 1. Here we'd have to figure out 8 of the terms. Well, actually 9, because you'd have to go 0 all the way up through 8. So, you save yourself a lot of work. Okay? Alrighty. That's it for today.